Okay, so yesterday we talked about this Brownian motion. So we had two description of this process. So one was the what we call Lanzwa description. So which basically describes how the trajectories of this Brownian particle evolves in time. So that's given by this equation, dx dt is equal to some noise. Okay, so it says that the velocity of this particle at each time is just random, and this noise has this property that its mean is 0. So it's a Gaussian random variable with 0 mean, and the correlation is given by the strength is 2D times Dirac delta function, right? So then we said, okay, this equation describes the trajectory of this particle. So we also had a description for the probabilities. So what it does is that suppose it starts with some initial position x0, this equation will describe how does each trajectory evolves and reaches some time. So this one will tell that if I start with some position x0, this equation will tell you that how this particle goes, and at some final time it reaches x. And this final position is a random variable, right? Because if I take, even if I start from the same position, because this noise is random, so it will take a different path. So maybe something like that, and it will reach somewhere there. So therefore this final position at time t, it's a random variable. And you can ask again, how does this, what is the properties of this random variable, right? So there is a probability associated with this, or we call it probability density, because the probability that it reaches between x and x plus delta x is given by this probability density times dx. And we had a description about how does this probability evolve in time. Okay, so that description is called Fokker-Planck description. And we saw that for the case of this Brownian particle without any external force, that's given by this equation, which is the diffusion equation. Right? So this is given by this equation. Then you are supposed to solve this equation, right? How many of you have derived the solution? Okay, one I can see. Okay, there are a few people. This have done. So what you should have found is that if you start with a fixed initial position, so it's that P of x0 is some fixed initial position. So then the solution is given by Gaussian. P of xt is given by e to the power minus x x0 whole square by 4 dt divided by square root of 4 pi dt. Right? So that is the solution for a fixed initial point. But then again, if you start with a initial probability distribution, then you can write down the solution as a linear superposition of this solution weighted with the initial position. Right? So this is what we did. So this is a Gaussian distribution. So there are some very interesting properties of this Gaussian distribution. Okay? And this one, so I'm going to show, because that's a bit useful. And see this one, so suppose I want to find out what is the probability distribution of x at time t, right? So what is this x at time t? So if I take this equation, let's put x0 equal to 0, but it can be anything, right? So then at x time t, it's just the integral of the right hand side, right? So that's given by 0 to t prime dt prime. So this noise eta, it's a Gaussian noise. So the distribution of eta is Gaussian. That's what we said, with this mean 0 and this variance, right? So there is a very nice property about this Gaussian distribution. So it says that if you take any superposition of Gaussian random variables, the sum is again a Gaussian, right? So how do you show it? It's very easy to show. Okay, so let's just, instead of this integral, because you know that how to, this integral you know how to also write down in the discrete form, because I showed you yesterday what is the discrete version of this equation. So let's just look at a sum, which is, let's say, sum over some discrete random variables, okay, of n of them. So you know how to put, how to relate n to t. You have to basically scale it properly. But suppose this is that, and the distribution of eta is given by a Gaussian distribution. So it says that distribution of eta is given by, so here I have taken the mean to be 0 and the variance to be 1, but you can take any mean and any variance and you can just generalize it. Okay, so this is for simply, or you can, okay, so you can just put a variance, it doesn't matter, right? Some variance. And it need not be also from the same distribution, it can have different Gaussian distribution with different variances. Okay, so for the time being, let me just remove this variance. So then how do you show that this distribution of this x is again a Gaussian? Okay, so what you have to show, so what is the Fourier transform of this distribution? What yesterday Abhishek said, you multiply by e to the power I k times this one and then integrate this. So that's also called the characteristic function. Okay, so it says that this is the expectation value of I k, this object. Okay, so this is same as minus infinity to plus infinity d eta e to the power I k eta e to the power minus eta square by 2 square root of. Now this is an integral you can do. So all of you know how to do a Gaussian integral, right? So now this is, you have something eta square, and then there is a linear term in eta. So what you can do is you can just make a complete square, and then what will come out is e to the power minus k square by 2. So if you add a e to the power minus e to the power k square by 2, you add and subtract, this will come out. So inside what we will have is an integral minus infinity plus infinity d eta by square root of 2 pi e to the power minus eta minus k whole square. So you can verify. This is eta square by 2. Eta square by 2, that's eta square by 2 with a negative sign. Correct? Plus. Correct or no? Oh no, sorry. Let's just. Now it's okay? So eta square by 2, then this will give me plus k square by 2, that cancels with this one, and then this will give me ik eta. Okay? So now this one, again, you can just make a shift in this variable. Okay? And then you know that this Gaussian is just it's a normalized distribution. So if you integrate with the distribution, this will give you 1. So this whole thing is equal to 1. So this is the answer. Right? So it says that the characteristic function of this one is given by this one. So now you have to find the characteristic function of this one. So you do the same. Right? So now if you do e to the power I k x, so this is e to the power I k sum over eta i's. But each of them, these etas, they are uncorrelated. Right? They don't depend on each other. So therefore this, okay, so this one is same as I e to the power I. Okay. This is J, let's call it J. Each of these are uncorrelated, so you can just take it, do it independently, and there are n of them. So it's just something to the power n, and a characteristic function of one of them, and that's just given by this one, e to the power minus k squared. Okay? So you see that this is again a characteristic function is similar to this one. So this one was e to the power minus k squared by 2. Okay? Except there is a n hanging there. Okay? So this n is like, so if you just take k square root of n as one variable here, so then you see that it's like, if you take k square root of n here, this is x by square root of n. So x goes like square root of n. Right? So it says that the distribution of x, therefore, again a Gaussian distribution with a variance which is n. Okay? So this is also now true for this integral, because you can just, from the discretization, you can again go back to this integral form with this proper scaling. So it says basically that if you take any linear combination of Gaussian random variables, the whatever is sum, so that's again a Gaussian. So that's a very nice property. Okay? So this is different from central limit theorem, right? So how many of you know central limit theorem? Okay? Okay, so all of you know the central limit theorem, so I'm not going to do it. So what central limit theorem says that if I take a sum of this form where these etas are drawn from some distribution with a finite variance, okay, then the distribution of x at a scale of square root of n is given by Gaussian. Okay, like yesterday you saw when Abhishek was doing this random walk, right? So when you scale it with square root of n, so initially you had this binomial distribution, but if you look at the square root of n, that's given by a Gaussian distribution. Okay, but the full distribution is not Gaussian, only if you look at it that scale. But for a Gaussian random variables, the full distribution is Gaussian. So this kind of distributions, so where if you draw a random number from that distribution, you draw some multiple random numbers from that distribution and you add them up. Again, if the distribution of that object is the same distribution, right? You draw from Gaussian and you got a Gaussian. So those kind of distributions are called stable distributions. Okay? So these are called distributions. Okay? Means the distribution doesn't change under addition. Okay? So this is the only stable distribution for random variables whose variance is finite. So if you take any random variables, the finite variance, and you add them up in sufficient number, it's going to converge to this Gaussian distribution. But for other distributions, if the variance doesn't exist, variance is infinity, so there are other stable distributions which are called Levy stable distributions. Okay, there is a infinite number of stable distributions. Okay, but this is the only stable distribution for a finite variance. Okay, so that's why you see this Gaussian distribution everywhere, right? Like when you do an experiment, for example, and you take data, you take n number of data, you add them up, and if you look at the fluctuations, that's always given by Gaussian distribution. You say Gaussian fluctuation, right? That's because you add things up, and these are uncorrelated or very weakly correlated. Okay, so now this property says us that, okay, it immediately tells me that the distribution of x should be Gaussian, right? That we know, but suppose we didn't solve this equation, right? We could have just started with the Langevin equation, and we could have written down the solution directly without solving this Fokker-Planck equation. Because that's a linear equation. Means that x is given in terms of the linear combination of the noise. Okay? So since it is a Gaussian distribution P of x, so for the Brownian motion now, so its P of xt is Gaussian. So Gaussian means that it only depends on two parameters. One is the mean and another is the variance. Right? So it's basically given by something like exponential of minus x minus the mean whole square by 2 sigma square root of 2 pi sigma square. Right? So what we have to do, we have to just find out the mean and the variance. That's all. Right? We don't have to do anything else. So what's the mean? So even if you don't start with x0, so it would have been this plus x0, right? The full solution would have been this one. So let's just take the x0 equal to 0 case. Okay. So what is the mean? So we are looking at this equation now. Okay. So what is the mean? Mean is just 0 to t dt prime right? But we know that this is equal to 0, so therefore this is equal to 0. What is the variance? Since the mean is 0, it's just variance is just the second moment. So what is the variance? So I have to write two of those. Right? So there's just the two integrals. So let's call one integral, the dummy variable is t1. The another integral dummy variable, let's call it t2. Same limit because they have the same limit. And then I have this eta of t1, eta of t2, and the expectation value. Right? So this one we know because that's given by this delta function. Right? So then I can just put it here. So this one is 2d delta t1 minus t2. So now I can just carry one of the integrals. So what does it give? 2d, one of the integral goes away. Then you have that other integral there is no argument, so it's just the integral, so that integral just gives me t. So this gives me 2 dt. So this is my sigma square. So now you immediately see that this is given by e to the power minus x square, sigma square is 2, so this is 4 dt divided by 4 pi. Right? No. So what we are assuming is this noise is a Gaussian. So that's an assumption. We're saying that the noise is a Gaussian noise. the distribution of eta is Gaussian, right? So given that the distribution of eta is Gaussian, the distribution of x will be also Gaussian. Okay? So now, this is what we got. Okay, this is a simple problem because anyway, we have already obtained the solution, right? So what is the point of showing this again, solving in another way? I mean, you already know the solution from a different method, right? So what's the point of showing that you can also do it this way? The point is that this fact that the sum of Gaussian variables is again a Gaussian, you can use it for other problems. Okay? So for example, this is a problem where there is no external force, right? But now we can put an external force. And we can ask the same question. What will be the distribution? Okay? So for example, the simplest way you can put an external force is you just put the particle in a potential where there is some particle position, and let's assume that this potential is given by half kx square. It's a harmonic potential. So this Markovian assumption is basically saying that this eta, this noise, right? These noises are uncorrelated. The eta makes the jump, right? So whatever this eta 1, or let's look at the discrete one, eta 1, eta 2, there's no correlation between them, right? So this goes into here, basically. So there's no correlation. So every time whatever the kick the particle gets, it's in that force is independent of whatever the previous kicks it has got. So this is so the particle is in this potential. So I have not told you how to derive the general Fokker-Planck equation yet. Okay? But I guess we can write down the Lange-Bach equation directly, because as I told you yesterday, Lange-Bach equation is kind of like a Newton's law where you have thrown out the inertial term. Right? So the Lange-Bach equation is therefore dx dt. See, this one comes with a, in the full under-Dam equation when you wrote down, it came with a gamma dx dt, right? Then you put it on the other side. So this is equal to, then there is this inertial term which you have dropped, right? So this is equal to the other forces. So what are the other forces now? So this will give me minus kx, and then the noise, right? But noise strength will be slightly different because that noise was divided by gamma. So let's just take this gamma from here and just put it here. So then it's just the same noise, right? So I have not told you how to write down this corresponding Fokker-Planck equation for this Lange-Bach equation. But this, again, you looked at, this is a linear equation. And this noise, eta, is drawn from Gaussian distribution. So what is the solution? X of t. In fact, okay, let me just make a remark before solving this equation. So you remember yesterday we wrote down another equation, the full equation for the velocities. So what was that equation? That equation was m dv dt, this is equal to minus gamma v plus some noise. Right? This is what we wrote down yesterday. So you see that this and this is the same equation. Right? These parameters are different. So you are supposed to solve this equation yesterday, right? So it's the same equation. If I know the answer for this, I also know the answer for this, or vice versa. Okay, let's solve this equation. So what is the answer? Because this is just the first order differential equation. So all of you know how to solve this equation, right? So what is the first term? X at t equal to 0. Exponential of minus k by gamma t. Right? All of you know how to solve these equations, right? You just multiply by this integrating factor and then you solve. Right? Should I do it or you know? Huh? Yes or no? Okay. Then what is the next term? 0 to t dt prime e to the power minus k by gamma t minus t prime eta of. So that's the solution. So now you again see that this x depends linearly on this noise. Right? So I could have actually put, I could have put some coefficients here. It doesn't change anything because as you have seen in the derivation, that it could have changed this different terms with different things. So instead of n, it would have been something else. Right? But it would have been still of the same form. Okay? So this is what you have. So now you know the distribution of x, therefore. So what is the distribution of x? It's a Gaussian again. Gaussian mean is given by this. Of course, where mu you have to compute and sigma you have to compute. Sigma square you have to compute. So mean is very easy to compute, right? Because the mean of this object is 0. So therefore this is just given by x0 e to the power minus k by. So you see that just it starts with x0 because that's where your particle starts, and then it drifts to 0. So this one you have to compute. Right? So how do you compute? Compute the same way we have computed this here. Okay. But now you have this extra term here, and that you have to take into account. Right? So I leave it as a homework. Right? It's the same. So this is also, you can just write as x minus the mean whole square average, right? This is the sigma square. So therefore, what is sigma square? I again have these two integrals. 0 to t dt1, 0 to t dt2, and then I have this thing e to the power minus k by gamma t minus t1, then I have this term e to the power minus k by gamma t minus t2, and then so this is again 3 delta T1 minus T2, right? So now you can just do these integrals and then you have to find the answer. Right? These are exponential functions, so you just find the answer, whatever the answer you have. Right? So then you know that you could basically have just derived this distribution for all time, just few steps, right? 5, 6 steps. So what do we expect when t goes to infinity? When you derive this answer, what do we expect? Should go to e to the power minus half kx square by kbt divided by the partition function, right? So partition function is just the integral of the numerator over all x, right? So you should verify that it goes to this distribution. Okay. Therefore, any linear process, any process which depends linearly on the noise, you can directly write down this this distribution directly without solving the Fokker-Planck equation. Okay, so that's a very easy way to do things, right? In fact, okay, we'll come back to this Fokker-Planck equation later. What is the Fokker-Planck equation for this problem? Okay, the second remark I want to make is that look at this equation. Look at this diffusion equation now. This is a second order in space and first order in time, right? So let me just write down the equation there again. Right? This is the equation for the free particle. Right? Without any potential. That was the equation of the free particle. There is a similar equation you have seen elsewhere, which again have two space derivative and one time derivative. So what is that equation? It is a Schrodinger equation. Right? So what is the Schrodinger equation? For free particle, what's the equation? Okay. So these two equations, they look almost similar because this equation has two derivatives, one derivative time is similar. Okay, it's slightly different, so we can but make it such that they look exactly same, right? So what we can do, we can just take out this minus sign here, and then we can just write this equation as del psi del of I by h cross d. This is equal to now they are exactly same. Your P goes to the wave function psi. Time here goes to a imaginary time in the quantum problem, and the diffusion coefficient D goes to this goes by WM. Okay. So this second and third, this two mapping, they are true always, but this mapping is only for particle. And if you have a potential, then you have to put something else. So we'll see this. But this correspondence is just another way of looking at this thing. There is nothing quantum about this problem, but it's just another way of looking at this. It's basically like a quantum particle in an imaginary time. Okay, and you know you have solved a lot of quantum mechanics problems, and you can use all these things. Right? So this is a useful thing to keep in mind. So now the other one, so here we have done a particle in a potential, right? So now this kind of problems, how do you write down the Fokker-Planck equation? Right? So you have to write the Fokker-Planck equation. How do you do that? So general derivation of the Fokker-Planck equation. Right? Okay. So as I said, Fokker-Planck equation, when you write down, these are for continuous random variables for Markov processes. Right? So Markov processes mean if you know the process at this instant, you can immediately tell me what will be there in the future instant. Right? You don't have to look at backward. Okay. So now, suppose you have a process where you have this variable x1, x2, xn. Right? In an n-dimensional space. So in the n-dimensional space, it's a Markov process. Okay. So for example, let me just give an example. Suppose I want to find out how does a Brownian motion, the Brownian motion in a potential, but not in the underdamped limit, in the full description. Not in the overdamped limit, but in the full description. Right? So I have to write down this equation plus the force term. Right? So for example, plus the force plus this noise. So let's just look at this example for a time being. Then we'll go back to what is x1, x2. So suppose I want to find out how does the position evolve for this Brownian particle, not in the underdamped limit, but let's say even at a shorter time scale. Okay? Then I have to write down this full equation. Right? So this equation, I can also write down 2 plus gamma noise, right? So this equation has two derivatives in time. So therefore, if I want to know x at some time t, just knowing x at the previous instant is not enough, because there's two derivatives. So I need to know x at t minus delta t. Also, I need to know x at t minus 2 delta t. So therefore, this is not a Markov process in x. So that's something that we can say it's a second order Markov process, or if I define the Markov process saying that it just depends on the previous instant, then it's not a Markov process. It's just a matter of definition. What I call Markov process, what you'll call Markov, right? So this is not a Markov process according to the definition I have given. So therefore, I cannot write down a Fokker-Planck equation for P of xt. But what I can do, I can use two variables. So instead of this, I can write down an equation which is dx dt is equal to velocity and dv dt equal to this one. Right? So now I have two variables instead of one variable. So now I can look at it in the xv plane. So these 2 points in the x, so in the x-axis, earlier I was trying to describe only in the x-axis. So there are 2 points, but now I can tell you x and v. If I just tell you x and v at some instant, it will give me what is the next x and v. Right? So it is just described by a point now. And this point will determine where the particle will go at next instant. So therefore, I need to know x and v only at one point, then I can know at another time. So this is a Markov process in the x v variable. So P of, I cannot write down the Fokker-Planck equation for P of xt. So this is no equation. But what I can do, I can write down an equation for x vt. So for that, I can write down a Fokker-Planck equation. So this will be a now variable of two random variables, because both x and v is a random. So there are two variables. So similarly, I can have n random variables which describes my process. So that will be in the n-dimensional space. So this is in the two-dimensional space. So that will be in the n-dimensional space. But the process, if I just look at only one of these variables, will not be Markov process. Okay? So another question is, how do you write down a Fokker-Planck equation for this system? Okay? So we'll do the same thing what we did it before. So P of, so this object, let me just call it vector x, right? So I want to find out this at time t plus delta t. Right? So we do exactly the same thing we did before. So P of x minus delta x at time t. So this is the, in this n-dimensional space, this is the position at the previous instant. Then I have to write down the probability density of jumping from x minus delta x to x. Okay? So there's this object in time delta t, it jumps from x minus delta x to x. Right? So earlier when we derived this, we assume that phi is only a function of delta x, right? Because it is homogeneous, right? But now, it actually not, if you have, in general, it's not only a function of only the jump, also from where it's jumping from, right? For example, if it is in a force, if I'm very far away, it's more likely to jump than I'm here, right? So therefore, it's a function of both x minus delta x and delta x. And then I have to integrate over. This is a multidimensional integral. Okay. So this is the integral over all component of delta x. This is what we did. So last time we just took a Taylor series expansion of this object because this phi was independent of the starting position, x minus delta x. But now both are function of x minus delta x. Right? So what we are going to do, we are going to expand both of them together. P times phi, you can just call it something like f of x minus delta x, right? I'm just keeping the, whatever the variable about which I'm expanding, okay? So now, what is the expansion? It's a multidimensional Taylor series expansion. So what is the expansion? This expansion is, okay. Huh? Yeah. So first term is this one. So second term is, yeah, grad f dot h. So let's just write down component wise. So this will be just 1 to n delta xi, right? That's a grad of grad f dot this one. So what is the next term? Of so on, right? So now, as we have seen that these higher order terms don't contribute, right, which we can a posteriori verify, so we are not going to write down those terms, right? So now this f, just look at this f and look at the integral, right? So f has two parts. So what is f? What is f of x? F of x is p of x times phi of x delta x, right? This is what f is. So now I can just go on and do the integral one by one. The first integral gives me what? First integral is just p times phi. P comes out of the integral because this integral is over delta x. So therefore the first integral just gives me p of xt. What is the second integral? The second integral, so let's just look at the, let's just look at this term somewhere here, a bit explicitly. So what is the second integral? So this is the integral over delta x. Then you have this delta xi. I'm just looking at one of the terms. Then I have this object, del xi of p of x, phi of x, delta x. So this is what I have, right? So this one is with respect to xi and the integral is with respect to delta x, right? So these are different variables. So therefore this one I can just take it outside the integral. So therefore this one I can write del xi, that I take it out. This is the integral with respect to delta x, so p doesn't have delta x, right? So this is, this derivative I have pushed all the way to the left. Okay. Now what are the terms? P of x is there, and that this integral. Times phi of x times this object. Right? So this is what we have. But this one we know that this is just the expectation value of delta xi. Right? So this is equal to just the expectation value of delta xi. So therefore, the second term will be of this form. The second term is there's this sum which is, I can put all the way to left. Then I have this object del del xi times this expectation value which is inside times p. Which is inside. Similarly, I can do the third term. So third term with two derivatives. I'll put the derivatives all the way to the left and then do this. So there will be delta xi, delta xj. So this will be something like del 2 del xi del xj times delta xi delta xj expectation value. So as you see that basically this derivatives works on both this expectation value as well as the probability, which are both inside, right? Because these expectation values, they may depend on x, the positions, and in some cases they will depend on the positions, you will see. Okay? So they depend on both. So now, what is the Fokker-Planck equation? So Fokker-Planck equation, we know that we just this thing on the left hand side divided by delta t and take delta t going to zero limit. Right? And then we'll assume that all the higher order terms basically they go to zero in that limit. Right? So then what is the Fokker-Planck equation? This is del p del t. This is equal to, it's coming from this one. So this one is minus I equal to 1 to n del del xi of this object delta xi expectation value divided by delta t. These are all in the limit delta t going to 0 times p, which is a function of x and t, minus plus of I j expectation of delta xi j divided by delta t times p with the limit that delta t goes to 0. Right? So I should put basically limit delta t goes to 0 here and limit delta t goes to 0 here. So I have to evaluate this in the limit delta t goes to 0. I have to evaluate this in the limit delta t goes to 0. So this is my general Fokker-Planck equation for a general Markov process. This is general Fokker-Planck equation for a Markov process. Now let's look at this problem of Brownian motion in a potential. So here we looked at the quadratic potential, but suppose we just look at this problem in a general potential. Okay. So what is the Fokker-Planck equation? We have to just compute those moments. That's all. Right? Once we compute those moments, we know everything. So let's just write down the equation. It's okay. Let's just come here. Huh? You can write down. Yeah, it will be just a function of time. Those things will be. Right? The question is whether you can solve it or. So now let's look at this equation now with a force. Okay. So if you write down this equation with a force, so what is the equation? So let me just write down explicitly. So there will be a force term, right? So what is the force term? So let's say this particle is in a potential which is u of x. So there will be an extra term here, right? So what is that extra term? So as I said, if I define it this way, there is a gamma here, so it was divided by gamma. So there is this 1 over gamma times u prime of x, right? So I'm assuming that it's a conservative force, but if you have some other force, you can just add it there. So I'm assuming that this force you can just derive from some potential. Yeah? But if some other force, you can just, in general, you can just put some f, right? F of x. So all the force term just goes here. So now I want to write down this equation. So what is the equation? I have only one variable. Right? So what is the Fokker-Planck equation I should write? So P of xt. Right? So what is the equation? You just look at one variable. Del P del T. That's equal to is the first term minus del x of delta x expectation value divided by delta t. These are all limit delta t goes to 0 times p. Then the second term, which is, so what was the second term? The second term was half. Since I have only one variable, this will be del 2 del x square times delta x square by delta t. So limit delta t goes to 0 times p. Right? So I need to find out only these two expectation values. Right? So how do I find it? So I have already told you how to discretize this equation. So what is the discrete version of this equation? The discrete version of this equation will be, if I write down delta x by delta t, right? So this noise has a variance. This delta function becomes 1 over delta t. So I can just put it, okay, so let's just call it no. So, no, see, the question is, what do you want to study? So if you want to study both, if you want to study the underdamped problem, right? So if you want to look at it at a shorter time scale, then you need to keep the inertial term. So in that case, it's not a Markov process. You have to write down an equation for both x and v. But suppose I want to look at again a time scale which is larger than m by gamma. So it's still a overdamped equation, but I'm just looking at inside a potential. The particle is in a potential. Right? So I have thrown out this inertial term. So now this is a Markov process because this is a first order derivative. Okay? So you have to just look at what is the order of the derivative. Right? It's a first order derivative, so it's a Markov process. Okay? So now del is, it's again a noise minus 1 over gamma u prime x. Okay? So now what is the mean? If I compute the mean delta x by delta t, the mean is 0. So this is just minus 1 over gamma u prime x. So what about the variance? So I multiply by square it, this equation, and look at the expectation value divided by delta t square. So this one is, so one is this object, then other is this object, then the other is the cross term, so this is equal to 0, this is equal to by delta t, because that's the discretization of this one. So this has becomes 2d by delta t. Right? So now, but what I need is delta x square by delta t. So therefore what I have is that delta t, so in the limit delta t goes to 0, right? So this one what we have is so I multiply by delta t on both sides, right? Because this is what I need, there is a delta t square. So this delta t will go, so this will give me 2d. This will be multiplied by delta t, but in the limit delta t goes to 0, s goes to 0, so this is what I have. Okay. So then what is the equation then? What is the Fokker-Planck equation? The Fokker-Planck equation is del p, del t is equal to, there's a minus sign here, there's a minus sign here, so that goes away. By gamma p plus 2d, there's a half there, so it says d. Okay, so this is the Fokker-Planck equation for a Brownian particle in a potential. Right? So we know the solution when this U was a harmonic potential, so that is Gaussian, but in general it is not Gaussian. Right? Because in general, this will not be a linear function of x. So therefore this equation is not a linear equation. Okay? So I cannot write x as a linear function of the noise. So I have to solve that equation, Fokker-Planck equation. Okay? So when u prime x was 0, that was again a simple equation, that was a diffusion equation, right? But this is a general case. And we saw that for that case, when u prime was 0, there is a analog to the Schrodinger equation. Okay? Can we find some analogies to Schrodinger equation? What is? Because for general potential, I mean, you have solved the Schrodinger equation for many potentials, you know the answer, and if you know some answer in the Schrodinger potential, so you might be able to use it here. Right? It's instead of solving the problem again, basically it's just reading the answer from if you already know the answer. Okay? So can we write down a Schrodinger equation, Schrodinger-like equation? So what is the Schrodinger equation in a potential? So what is the equation? Right? That's the equation, right? So what we did in that transformation, let's just do this. Let's just do the transformation of time. So transformation of time when we did, so we have taken a minus sign this side. So this was like del of I by h cross t. This is equal to a square by 2m minus. Right, so that's the Schrodinger equation. Okay. So we can of course do transformation time goes to I by h cross time, then d goes to h cross square by 2m. But we cannot do a simple transformation where p goes to psi, right? Because there is no first order derivative in the Schrodinger equation. Okay? So therefore we have to get rid of this first order derivative term. Okay? So how do you get rid of this first order derivative term? So what you do is p of xt, you define something called phi of some function of x. Okay, it's not that phi, it's just some function I'm just putting, called it g of x times psi of xt. And put it in this equation. Right? So what kind of terms it's going to generate? G is a function which you are going to determine later. Is it what kind of function? There's some function I am going to determine which makes my equation looks like this one. Okay. So what kind of terms, when I take those derivatives, what kind of terms it will generate? It will generate some terms. Okay, there is a term which is del p del t that's going to act on this, right? So on the left hand side, it will be just g of x times del psi del t. So where this term on the left hand side, I can just put it to the right hand side and it will be just 1 over g. Right? So this will basically give me some equation which is del psi by del t. This is 1 over gx times something. So there will be a lot of terms. You have to compute all these terms. But there will be some term which will be, so like for example, what kind of terms it generates? Suppose you take a first derivative of this one. There will be one with respect, now it's everything with respect to space coordinate, right? It will generate a term which is first derivative in this, and then it will generate a term which is first derivative in this one. Okay? You do the second derivative. It will generate something, first derivative here, second derivative here, nothing here, second derivative here, something here. Right? So there will be some terms. So what is the form of these terms? So there will be some terms where this will just come without any derivatives. Right? So this will come as psi of xt. Right? So please do the calculation. Right? Then there will be some term where this thing will come as a first derivative. Right? So there will be some terms where this will become like So inside, what we have is some g prime, some function of g and g prime, right? So inside even here you have something contains g prime, g double prime, right? So similarly inside here you will have g prime, maybe there cannot be any g double prime term, right? Yeah. It will contain some terms which contains these guys. Then there is a term which is the second derivative term. So there is only one second derivative term. That's basically the second derivative of this one, where you don't act on g at all. Right? So the second derivative term will be g times psi double prime, and there is a d here. So d right? This is what you have. So now what you have to do, so now you look at your Schrodinger equation. So which are the terms there? So g is some unknown functions which we are going to determine. Okay? So which are the term there? Is this term there in the Schrodinger equation? So this term is there. So I'm going to keep this term. So this term is there, I cannot do anything. And see, this g actually cancels with that z outside. Right? So this term is there in the Schrodinger equation. That term is basically this term. Is this term there? This term is there in the Schrodinger equation because this term is this term. But there is a term here which is not there in the Schrodinger equation. So then what we can do, we can force this coefficient to be 0. So when you force this coefficient to be 0, so this will give me an equation which contains g and g prime. Right? So I have to solve that equation. That will determine g. So this equation basically give me g of x. So such that this term becomes 0, but this will be something non-zero term. Okay? So now this one, it turns out that this term will become, when you do this calculation, so it almost looks like the equilibrium distribution. So what is the equilibrium distribution for this particle in a potential? It's the Boltzmann distribution. So what is the Boltzmann distribution? E to the power ux by kbt. Kbt is your gamma d because here it comes in terms of gamma and d. So let me just write in terms of gamma and d. But it comes with a factor half. It just comes with a factor half. So what it means that if you knew how to do that, you didn't have to go through this thing. If you had used that transformation where you use this is equal to e to the power minus half u of x by gamma d and put it here, that's going to get rid of your this first order derivative term. Okay? But so therefore you have a Schrodinger equation now. So now P of xt is basically given by e to the power minus half x by gamma d times psi of xt, where psi satisfies the Schrodinger equation with this transformation with a potential which is not exactly u because there will be some other term coming here. So with a different potential. So you have Schrodinger equation with a potential v of x which is given by a u prime x whole square minus b So A and B are something which will be function of gamma and D. Some in terms of gamma and D you have to find out. Okay? So maybe okay, let's see what are these things. Yeah, maybe it's okay. Let me just see. Okay, I'm not very sure, but okay, this A is basically 1 over 4 gamma squared D, and B is 1 over. You just compute it and verify. Okay. But the point is that your quantum potential is basically not the classical potential, but in terms of the classical potential, you can write down the quantum potential. Right? So this is the we're still harmonic. That we already found. That's a propagator is Gaussian. Propagator is Gaussian. Right? Which one is a Gaussian wave packet and harmonic oscillator? In the harmonic problem, there are two things. The harmonic problem, there are two Gaussians. One is when you expand in the eigenbasis. Right? The weight factor is Gaussian, but then you have these Hermite polynomials. Right? These are polynomials in X. On the other hand, when you write down the propagator, all time going from some t to t prime, that's again a Gaussian. Okay? So that Gaussian propagator, quantum mechanics propagator, is that basically whatever the Gaussian distribution you found out, you have to do this back transformation where t goes to I by h cross t, and with all this thing, right? So that's the propagator. So this distribution is Gaussian. But now, so it's a particle in a potential, right? So you saw that in the morning's Abhishek class, so he did this master equations, right? So when you derive this master equations, so he looked at a finite system, right? It was a finite matrix, it was a finite system. So what happens there? What did he find? There is quantization. So what is the quantization here? So there is a quantization even here. Because this equation, either this one or that one, so this equation, you can just think of it like, okay, so what is the equation he wrote down? It almost looks like this one. Let me just... it almost looks like this one. So the equation was del P del T is some operator acting on P. Right? There he was calling it W. That was a discrete, that operator is a matrix there. But here this operator is not a matrix, it's a differential operator. Okay? So there is some operator acting on this one. So this operator is, for example, in this case, this operator, what is the operator? Is just given by del del x, u prime x by gamma, plus d del. So this is the operator, right? So now, therefore, P you can write down in the basis of this operator, right? And this operator, when you looked at in a potential, so this operator will have discrete spectrum, discrete eigenvalues, like the way you had there. This Fokker-Planck operators in this potential will have discrete eigenvalues and corresponding to eigenstates, right? So therefore, if we want to write down so what is the formal solution for this equation? So formal solution is that P of xt is equal to e to the power t P of x0, right? If I formally solve. So now I can expand this P in the eigenbasis of this operator the same way you do in the quantum mechanics. And if you have a discrete spectrum, so what you will have is you will have something like n e to the power lambda n t. Let's not call it psi because psi is we are using for this one. Some eigenfunctions, I don't know. Okay, let's call it this psi n of x and some an which we need to determine from the initial condition. So this psi x are the right eigenfunction of this operator. The same way you had the right eigenfunction for this your W matrix in Abhishek's class, right? And this an will be expressed in terms of the left eigenfunctions. Okay? And this operator L is not a Hermitian operator like the way you have in the quantum mechanics. And what we have done by this transformation, we have transformed to a problem where basically by some transformation we have gone to some another operator which is Hermitian. Because for the quantum problem, the operator is Hermitian, right? The Hamiltonian is Hermitian. Right? So that's what we did. But in a quantum problem, the ground state energy need not be zero. Right? I mean, for example, just look at the case of harmonic oscillator. What is the ground state energy? It's like half h cross omega. That's a non-zero. But here, we need the grounds. So what is the characteristic of lambda you should have? So what you should have is, one of the eigenvalues should be equal to 0. And all the other eigenvalues should be negative. Right? And so you should have lambda 0 is equal to 0. Lambda 1. So this shift, when you go from the classical to quantum, this shift makes sure that your ground state energy for this quantum problem is 0. See, this one, if you just consider the harmonic oscillator case, this term is still a harmonic oscillator, right? But there is a shift in the energy because this will be a constant. So this is just k by 2 gamma. So what you will find when you do this comparison, what you will find is that your k by gamma should be equal to h cross omega. Because half h cross omega is this thing. So that term cancels your ground state energy. So then it says that, okay, your ground state is this thing. So in the limit, when t goes to infinity, so you go to the equilibrium state. Right? So it's the same, almost same algebra. So there you find a eigenvalue for her matrix. So here it's like an eigenvalue of an operator. Also now, when you write down in this one, so what you can write is, you can see that this psi, you can write, so what is this thing? So you can also write P of xt as e to the power minus half by gamma d. Now, you expand in the eigenbasis of this psi for the quantum problem, right? So in the quantum problem, so what is the quantum problem? In the quantum problem, what is the equation? IH cross del T of psi is equal to this psi, right? So this one is psi is e to the power minus I by h cross t psi, right? Psi t is psi 0. So you will have is e to the power minus I by h cross, there's a h, the eigenvalues of this Hamiltonian, En. Then this one you are expanding in the eigenbasis. So this is what you are calling psi n of x, and then you have this En. So now you see that this negative sign is already there, and by h cross t you have replaced by time, right? So this I by h cross t in a quantum problem, when you go to the classical problem, that has become your time. Okay? So then you see that it's the same form, e to the power minus half of x by gamma d, and an e to the power minus t. This is now for the classical problem because I have to do this transformation, right? And then En times psi n of x, and these Ens are the energy. So now these are positive energies, so that makes you your lambdas negative. Right? So lambda is just minus En. Okay. So therefore you can write down this solution easily for the harmonic oscillator problems. What are these science? So En you know, En is just for harmonic oscillator. Let's look at the harmonic oscillator problem. Harmonic oscillator, also a homework for you to write down with the proper factors. So Ens are half n plus half h cross omega, but then as I said that this there will be h cross omega coming from here. So therefore in this case it's just n h cross omega. So h cross omega you have to express in terms of gamma and d and k. Right? Because the way you write down this thing is half m omega square x square. Here the way you have written down the potential is half kx square. Then h cross by 2m is your d. So you just transform into this thing. And then these are given by with the Gaussian weight. These are just the Hermite polynomials. And an, what is the an? How did Abhishek calculate an? Suppose you know the initial condition. How do you compute an? It's the overlap, right? So what you do is, suppose so this is the equation I have, right? So now, either this one or let's just take this one. This is the equation you have, okay? So now P, if I look at this equation and put T equal to 0. So I have to find an, right? Find an, okay? So let's assume that the particle starts with position x0, right? So if I put t equal to 0, so what I have is an sin of x, right? So now I multiply with the left, and then you have that. So I multiply by the left eigenvector. So this case left eigenvector is just a complex conjugate of this one, right, in the quantum one. Or I could have just gone to this one and I just multiplied by the left one. So there it's not the complex conjugate of this psi, right? But let's just look at this one. So what I do is P of x0 and then psi n star x. So what is P of x0? Delta x minus x0, right? So this is delta x minus x0. This is this one. I multiply with sin star x and integrate over x. So this one gives me, on the right hand side, I integrate over x e to the power minus of, let's do one thing. Let's take this term to the left hand side, right? So if we take this term to the left hand side, this is half u of x by gamma d. So this is equal to n dx an, let's call it m psi m star x sin x. But these are orthogonal, right? So therefore this is delta mn. So what we have is, therefore an is given by, this integral will basically make it x equal to x0. So this will be given by psi n star x0 e to the power half u x0 by gamma. Right? So now we can write down the full solution. So these are again because for the harmonic oscillator is just the Hermite polynomial and then this thing. So now full solution is P of xt is e to the power minus half. One is this term, one is that other term. So I can just combine the times infinity so this is a full solution. So where E0 is equal to 0, right? So E0, so En is just this one. You see that this, therefore, when you take t goes to infinity, this goes to, it should go to steady state. So what is the steady state? If you take t goes to infinity, E0 is 0, all the other terms are not 0. So can you tell me what is psi 0 now? What is psi 0? Yeah, but given that it's Gaussian, but even given that I know what is the steady state for this problem, can you tell me what is psi 0? So what is the steady state of this problem? It's a particle in a potential. It should go to the Boltzmann distribution. So then what is that? So this should go to, it should go to this one with normalization, whatever that normalization thing it comes, right? U is just half this thing, but so in general, this is not Hermite, it's not Gaussian in general. No? only for the harmonic oscillator is Gaussian, but in general it's not Gaussian. But what is psi 0? We know that E0 should be 0 for in general. E0 is 0, not only for the harmonic oscillator problem, but for all problems where your potential is bounded, so that the particle gets trapped there. And what is psi 0? Let's say initial condition is your start switch 0. So what is the meaning of a steady state now? Will the steady state depend on the initial condition? So it will not depend on the initial condition, right? So therefore, this term should be, this is x0, right? This one is x0. So this term should be cancelled with this one. And this term together should give me this one. So this should be proportional to e to the power minus ux by 2 gamma t. Huh? Yeah, but you see that it will cancel that one also. This is the same term with a negative sign. So one term will be added and make it 2 becomes 1 and the other term will be cancelled. So this should be your ground state wave function. Right? What is what? The other ones you don't know. Other ones will depend on the problem to problem. But what you know is that you can write down this one. Because ground state is something for this kind of problem, it's easier to solve. Right? So you can in fact solve for the ground state very easily from this problem. Right? What do you have to solve? Steady state means that this left hand side is equal to 0. Right? So what is the solution? So you have to solve this right hand side equal to 0, this thing. And so when you solve this one, now the steady state, so this one, that solution, whatever I told, I just argued because that should be the Boltzmann distribution. But you can also just find out from here. Right? Steady state. Okay. Del P, del T is equal to 0. So this is, if you write down del X, right? This is what you have. So it says that this guy is a constant. Right? So that's a solution. Now what is this constant? This constant, now this is some particle in some potential. Right? So you expect that, so you don't expect to find a particle at infinity. Right? So therefore P of x at infinity should be equal to 0. So there's no time now. This is a steady state solution. So you expect that P steady state at infinity should be equal to 0. Also the derivative should be equal to 0. Or in other words, this term is like a current, right? This is a diffusion current and this is a drift current. So the total current at infinity equal to 0, because if the total current at infinity is not equal to 0, then things will leak out to infinity. If things leak out to infinity, you will not have a steady state solution, right? So therefore, that also you can say, so this constant is equal to 0. If this constant is equal to 0, these are just a now ordinary derivative because there's no time. So then what is the solution? You can see that immediately it's a first order equation. You can just write down the solution. And the solution is P steady state is given by some normalization constant e to the power minus the integral of this one. So this is ux by gamma times d. So this is done. And this one is basically given by just the normalization constant, right? So it says that Ps x dx minus infinity to plus infinity, this should be equal to 1. So that fixes this normalization constant. So this is basically this given by. So you see that your Boltzmann distribution basically just comes out of your Fokker-Planck equation, right? So as it should be. Okay. Okay, let's just stop here. Maybe if you have any questions. So these ones, see there is there at various places, like for example, you can, I think look at Van Kempen, I think there's a book by Gardiner, then Risken, and also I have some lecture notes which is linked from the last school. So if you just go to this last 2017 school lecture notes, these are just handwritten lecture notes. So if you sit in the class, then you will know that, okay, whatever this thing there. So it's not, there's not much text, but the derivations are there basically. I think you'll probably, yeah, I think you'll find it in Risken probably, yeah. Yeah, or any, yeah, other books will have basically. Gardiner book probably will have, yeah.